Thank you very much for the introduction. Yeah, as stated, I'm a physics and mathematics researcher in Canada. I have elected today to speak about a topic which I think is relevant to many people's interest, specifically in the context of singular learning theory and some of the other energy-based attention models that were discussed earlier today. So by contrast to many of the previous presentations, while this talk does concern a great deal of computing itself, it's really more of an introduction to geometric phase in topological matter and sort of what the relevance for something like that would be. So the yeah, our talk today will cover just a few basic concepts related to sort of the underlying required models or information in order to sort of proceed with this theory. Namely, some of the basic topological notions that we'll be exploring, because in fact, we are considering a form of quantum computing in which the properties of the certain geometric quantities associated with the very physical aspect of computing, it plays a very significant role. So this is a description, could be considered an introduction to so-called topological quantum computing via the knot theory. Although we will be mostly considering the practical implication of running superconducting quantum computing modes involving Majorana fermions, and the notion that they can be used to store cohesive information states, specifically in certain kinds of topological insulators and semiconducting materials. So as a basic introduction to some of the concepts that we'll be looking at, we're really not going to be considering any significant, really difficult concepts in mathematics outside of just a few simple notions of classification based upon sort of the behavior that certain geometric objects have with regards to their orientability or their surface topology. Basically, if you can understand what a band is or what a circle is, you more or less have everything you need in terms of the very most basic possible representation of a computable quantum material state. We mostly consider these simple objects, the circle or an object in S1, and the Mobius strip as the two most primitive sort of topological quantities. We note that if you place a norm on the outside of a circle, of course, it will never turn towards the center, and likewise, a norm on the inside of the surface will always point towards the center. Whereas on a Mobius strip, as the norm traverses over the surface, it does in fact change directions. So we tend to say that such a surface would be non-orientable. And finally, we have these two linked tori here, which will probably be the most complicated object that we're going to consider this evening, namely due to the way that we will be considering the geometry of the Ising chains in terms of the Kitaev model. But the torus shares certain geometric properties with both the circle and the torus, or sorry, and the Mobius strip, in the sense that the orientability of the norm becomes subject to where on the surface it is found. And also there's a direct relationship between the idea of traversing the circle according to, say, a figure-8 pattern, which brings the notion of the winding number as sort of a connection between the geometry of the Mobius strip and the torus itself. Okay, so basically, in the theory of knots, we are mostly concerned with certain invariant quantities. Here we are looking at the most simple representation of the invariant circular quantity given in the theory, which is just given in terms of a sum, in this case, a negative sum between two scalar values. And these basic rules of computation in terms of untying or being able to unwind knots really comes from just a few simple rules that we derive from these invariants. So the two that you see here are just effectively equivalent to each other under a rotation. And so this allows us to go back and forth between descriptions of these knots by merely rotating the knot operators. And that allows us to define invariant quantities, which are very useful for computing. So as we see here, we can reduce a complex problem such as twisting in a loop to simpler subproblems, which are consistent with our algebra of grouping the knots according to their invariant subquantities. And we see that even a very seemingly complicated or convoluted knot problem can in fact be decomposed in such a way that it becomes topologically equivalent to a circle. So that's part of the explanatory power of knot theory in this description, because it allows us to consider how simplified geometric primitives allow us to build complicated information states on top of them. So as our first foray into actual physics, we can consider a description of the qubits in, say, quantum computing as brackets. So here we see the bras for the 0 and 1 state vectors and the corresponding kets, with the arrow of time corresponding to what we will soon find to be very relevant to the path history in terms of an actual path integral formalism. So because our primitive elements in our computation have these geometric analogs, when we compose them, we can consider them in terms of certain invariant quantities. So we also see that upon measurement, so we can have a measured state which occurs at the junction of some form of superconducting material or topological insulator, in which discrete state quantities are taken at those interfaces, and a much more complex structure could be contained between them. And this is simply given to us in terms of the definition of the expectation value of the path operator for the braid, such that so in the corresponding photo to the right, these x's would correspond to state collapses with various measurements, which can occur discretely while the knot itself remains intact. This image would be corresponding from one configuration of the system as it undergoes transformation into another. So what's very powerful about this braid description now is we can generalize these so-called anyons, which anyons become the particular representation of these knots in terms of something corresponding to an operator in field theory. So in this particular case, we have the Pauli matrices and their inverses, which are given in terms of a set of braids, and each one of these braids corresponds to like a vector. So if the Pauli matrices are given in terms of SO2, so this would be like a braided state, a non-braided state, and then a mixed braided state with another mixed braided state, and then a non-braided state and a braided state and their corresponding inverses. And you can effectively make products of these Pauli matrices by applying Hadamard gate functions in a typical quantum computing circuit in order to produce certain kinds of invariant quantities. So here we see that the algebraic quantity, the product of the inverted first and second Pauli matrices with the first, is equivalent to the product of the so that would be the left-hand multiplication onto the first Pauli matrix is equivalent to the right-hand multiplication of the first and second matrices on the second Pauli matrix, which works in normal matrix theory. So this is consistent with what we would expect from the normal group algebra. What else is very attractive about the notion of using braids, so to speak, as modes of storing qubits is that they are extremely resistant to noise. So in this cartoon, we see that a braided state, a braided entangled qubit state, experiences noise on one of its channels. However, it does not affect the ultimate observable quantity associated with that braid because the noise can simply be wound out of the connection. So ordinarily, quantum information states, especially those in Bell states, tend to be subject to a lot of noise-related decoherence, which causes them to collapse, sometimes internally, sometimes due to environmental noise. What differentiates the quantum computation from everything else occurring outside of it in the universe becomes quite a little bit more difficult to define when you get into entangled states between operators. So there's sort of an inherent noise resistance and resilience found in the Anyon braided states of topological quantum computing, which makes them attractive in terms of realization of a practical quantum computer. So effectively, as we saw in the previous diagrams, the basic formulation of our braid is given in terms of the expectation value between some initial state and some final state, given in terms of path integral defined over some action. And that allows us to consider the actual computation itself not only as a sequence of say gate operations, but actually a space-time history. In fact, I don't go into this in the scope of this talk due to brevity, but there's a direct correlation between the path integral formulation in quantum gravity and at least according to certain formulations such as loop quantum gravity and causal dynamical triangulation, which sees this action here, S, replaced by the Einstein-Hilbert action, and you effectively have an analogous description for space-time histories in terms of gravitational influence as an analog to classical or to quantum computing. So this is an area of significant interest for me that I intend to see to fruition in the future. Coming back to our functional description, we begin to see effectively a description of computing which starts to resemble something that we might see in statistical physics or statistical computing regarding. So if you look at the top, this would be like the discrete formulation, which for a well-defined functional allows us to substitute as a smooth integral, at least piecewise normalized according to some constant n. Referring back to the earlier description in the Pauli matrices that we saw, so to consider all the possible interactions between paths of or braids of certain types. So here we have type +1, in which there is no direct interference between the braids, and then type 2, in which there is. So we see that we can look at the entire path history in terms of these different types of potential interacting or non-interacting braids or non-entangled braids in terms of nothing more than the some product of the different types, the sum of them taken over some range, which gives a very elegant, description of this path integral. Of course, we see in practice that looks can be somewhat deceiving, and the practical realization of computing these particles or these particle operator states in reality can be somewhat more difficult, but it is nice that the ultimate smooth field description does in fact correlate to a fairly well-behaved functional involving discrete summations. So if we're considering a classical geometric phase, like what, so now I guess I'll just quickly add. So now we're sort of pivoting away from the description of the data, the topological matter states themselves, and we're sort of now looking at them more sort of in terms of the actual material quantities, constraints, and parameters associated with them. So for that, we will consider similar topologies to what we saw on the first slide, such as a sphere and a Mobius strip, and we see that the sphere will admit basically any subpath that is isomorphic to a circle, and that includes the equatorial or any other sort of sub ring or sub loop taken on the manifold itself. Whereas the Mobius strip will admit the theta value that we see here just refers to just an angular vector along the closed path, which in this case is gamma. So this the difference here. You'll find that the analogy between the inverting norm in the Mobius strip corresponds to effectively the winding number in the when considering the phase. It will give you the sign effectively whether the orientation is positive or negative, corresponding to the direction of the loop, and likewise the geometric phase is referring to the deformations of the sphere will basically just give you the normal quantities that you expect according to Stokes' theorem. If we want to consider the effect of this change in angular phase on a physical system, we can consider an arbitrary Hamiltonian which has a set of state parameter values k. Please excuse the ugly LaTeX, by the way. This is due to Keynote not playing nicely with some of the formatting. I did my best to kind of clean it up, but some of these indices, such as k, should in fact be given bolded, but that didn't work for some reason. Nevertheless, so these you can find the eigenvalues n e sub n of k corresponds to family of arbitrary rotations in the system where a phase angle is introduced as you take the time or spatial derivative of the system, and it is from here that we extract the notion of a path phase angle, which is given here as gamma, which we will hereby refer to as the Berry phase. Now, this is a very important quantity that corresponds to the topological ordering of the system, although it was discovered sort of indirectly, kind of by various different mathematicians and physicists, until eventually the notion of geometric phase was sort of generalized into the idea of the Berry phase. And we see here that for the time-dependent Schrodinger equation, having time-dependent phase parameters k applied to some state vector can be considered in terms of something that looks a lot like what we saw before in our path integral, something like this sort of looks like an action quantity, which is shifted by some phase factor, which in this case the Berry phase actually becomes the angular shift parameter in the that corresponds to the eigenfunction for that specific value n. So it's a very powerful notion that extends a sort of concept of topological invariance to looking at interactions in quantum electrodynamics. And as such, the Berry phase can be further sort of the value of the Berry phase is further exploited in the notion of the Aronoff-Bohm effect, in which if we consider a particle confined to some region, in this particular case, a volume, which has some curvature tensor A, which is parameterized as what we call the Berry curvature. I left a lot of the differential geometry out of the scope of the talk for the sake of sort of big picture thinking, but effectively there's a curvature tensor which is gauge invariant in 3 dimensions, which we exploit by taking the position of the particle with respect to a closed loop R of t, in which in the presence of a magnetic field, so classically a magnetic field would be given as the curl of some vector potential A of R, then we find within an impenetrable flux tube the Aronoff-Bohm effect to be given by the Berry phase in terms of the charge value over Planck's constant, and some closed loop value. So this can be integrated over as an argument to an exponential, and usually because of classical analysis, namely Cauchy residue theorem, that allows you to evaluate the integral to, or the exponential to be 1. So again, it's a very powerful heuristic description that plays a fairly considerable role in a lot of cosmology and condensed matter physics, not to mention collider experiments in which the beam itself can be considered electrically or magnetically confined flux tube. So the Aronoff-Bohm effect becomes fairly important for potentially indirect or direct observation of magnetic fields in the presence of certain kinds of events. So if we further generalize the notion of the geometric phase, we can actually reduce it to sort of a equivalence and classification scheme in which the fiber bundle topology becomes effectively the sort of universalized manifold theory for the consideration of this path integral history over some projective Hilbert space. So if we consider the holonomy group in terms of a local one-form connection, then we see this P, our group is basically given by P times E to the Berry phase, which here is basically just given as a phase shift angle. Now, in abelian gauge theories, P is always equal to 1. But in non-abelian gauge theories, P can vary. Furthermore, we construct a fiber bundle in terms of some field operator, fermionic field operator in the space of our Hamiltonian, which gives us basically for all R in the parameter space, we get effectively a field shifted eigenvalue, which is confined to a single loop. So this holds for all N and R. Thus, we see that the Berry phase, which here given by e to the I gamma, is synonymous with the holonomy of the local connection of our potential A to N over this over some fiber lambda n, namely using a certain lifting property, which comes from mapping the principal fiber bundle via projective mapping to the density operator. We're able to obtain a curve which is referred to as the Aronov-Andon phase, which gives us the ground state operator of some projective operator in terms of the Berry phase itself. So this is a pretty useful result, especially when we start considering phase order topology. So, but in order to do so, first we need to actually consider the symmetrical properties associated with the Landau-Fermi liquid theory, in which low energy excitations of quasi-particles are mapped in a self-interacting Fermi system by free system of excited fermionic states. So effectively, that gives us a free energy term in which F0 is some smooth function of temperature, and FL is our Landau functional, which is really nothing more than an analytic function given as an expansion, as a polynomial expansion of the order parameter, which is necessarily invariant under symmetry. Now, due to Goldstone theorem, we want to consider the spontaneously broken continuous global symmetries associated with the quantities of our Ising ferromagnet. That gives us an opportunity to consider disordered phases of local group transformations as systems of charge-coupled spin-half fermions, which undergo spontaneous symmetry breaking as they transition to a superconductive state. So if we consider then a toy Hamiltonian version of an Ising ferromagnet, given in terms of a short-range electric coupling JI, we see almost immediately that there's a Z2 symmetry, which is invariant under time reversal, such that SI goes to negative SI. So the spins described by this Hamiltonian then tend to either spontaneously break up or down according to the average expectation value of the spin operator for the field operator. And from this, we can actually construct an effective quadratic theory based on this functional integral representation, sometimes referred to as the Hubbard-Strontovich transformation, in which we're looking at the way that the average value of psi changes according to the change in the expectation value for the spin operator. And although this looks a little bit unwielding, we are actually able to approximate the effective free energy f of t by a functional value in which we approximate z as just like the components in this term corresponding to the free field theory itself, which a free field theory of the Ising system, which dramatically reduces the computation and allows us to then yield an effective continuous Hamiltonian over the continuum field of psi of x in terms of this functional. So in which the only unknown quantity here, W, is given as some sort of parameter corresponding to velocity-dependent macroscopic parameter of the system. So it's not that important to include. And that Landau term is then given by this quadratic and quartic function for some constants, which are not too difficult to find, but not very necessary. So from here, we can actually consider the notion of entanglement entropy then, since the normal von Neumann quantity, entropy quantity associated with a certain set of subsystems A and B in the presence of a large boundary L can be given as such, in which the total quantum dimension is described. That's the gamma is described in terms of the log of the value for the functional, the step value of the functional given in the previous slides, and thus we have a fractional quantum Hall system associated with either an odd number of Q distinct abelian anyons having quantum dimension always equal to 1, or non-abelian analog anyons which have quantum dimension always given in excess of 1. So this allows us to consider topological ordering as a classification of short-range entangled states, sometimes referred to as symmetry-protected topological phases, when they have distinct parameters, topological parameters, but unbroken symmetries. So the most important aspect of this topological entanglement is that it's entangled at a long range. So that makes it very important to the notion of persistent data states, as we spoke about earlier. So I'm going to breeze over this very briefly, but so in superconducting systems, we talked briefly about the boundaries of topological insulators, and we talked about the braiding operator. But what we didn't talk about is what makes the entire thing possible, and that is the notion of Majorana zero modes. So Majorana particles are quite famous. They are effectively self-conjugate, which makes them equivalent to their own antiparticle representations. So as a result, they have commutation rules which don't, or anti-commutation rules corresponding to effectively summing over their respective delta functions. So the advantage to these, and of course, the particle creation state then requires that the second state has an imaginary value, so that we're able to get correct ladder operator behavior. But the real value to Majorana zero modes is that they correspond to topological banding theories in which the positive and so the negative state eigenvalues correspond to the positive state eigenvalues, such that the value for the configuration of a given system then becomes equivalent at the boundaries of the interaction points between these particle modes. And it should be noted that some effort has been taken to verify the existence of so-called Majorana zero modes in condensed matter physics, including 1D representations in superconducting wires, and they're very much a staple in many field theories, effective field theories, and descriptions of superconductivity in condensed matter physics. So they're very important particles, although to date no fundamental representation of them has yet been observed, although there's quite a lot of evidence that the neutrino and for sure the neutralino is in fact a Majorana particle, although verification experimentally remains to be seen. But nevertheless, these Majorana modes actually correspond to gapless quantum operators, which have a corresponding number gamma k, which is literally given by the Berry phase, which is the so-called Majorana condition, in which the time charge inverse of a standard fermionic operation corresponds to the Majorana zero conjugate for that kth state vector. So they're quite important in considering topological quantum computing modes, because effectively it's impossible to build associated braid states without these conjunctive Majorana modes that allow the states to effectively be linked to one another. Sorry, that was an accident. I suppose I should have just left it on here. But yeah, so those eigenvalue symmetries correspond to whole anti-whole symmetries as microconducting or as superconducting microstates along wires. So finally, we're getting into the last portion of the talk, which concerns the toric codes, which are generated by the Ising Hamiltonian. So here we have poly operators, so X and Z gates corresponding to logical gates in a quantum circuit. So for this point forward, we'll be considering an m by n lattice in which, like in 2 dimensions, we're able to define exactly solvable codes. And this becomes effectively the canonical example of a topological phase. So what's most interesting about these toric codes is that they allow us to find the underlying topological order of spin liquids, which are highly, like in a highly entangled topological state for spin half particles along some surface with genus G, as we described earlier. Thus, the emergent states, which are defined in terms of abelian anyons, give the so-called simplest quantum double and serve as a prototype for quantum error correction stabilizer codes in general. So if we look at the toric code specifically in terms of its representation as a Hamiltonian, which is summed over for all sites V, so V corresponds to the vertices, and P corresponds to the plaquettes, with positive couplings J and M. So J refers specifically to the electric coupling for some potential field vector A, and K here actually refers to the magnetic effective field coupling for some field potential B. So here we see actually the beginnings of a 2 potential electromagnetodynamic formulation of the of electrodynamics, but given in terms of an effective field operator, like I said, for some set of vertices and plaquettes. So those products with the plaquette operator corresponding to the electrical particles. I think I might have messed those. Might have messed the superscripts up, but anyway. So effectively, the particle operators associate with the respective electric and magnetic particle properties, and those are given in terms of some product of the gate values corresponding to the poly spin matrices. So for the vertices, we basically find, let me just verify that that's the same. Yeah, it's okay. It's fine. So for the vertices, we find that this vertex operator yields certain behavior if the number of spins in the system are down or are even or odd in terms of the number of down spins. So that gives a sign according to whether or not the number of states are dominated by even or odd values. And likewise, the plaquette operator corresponds to effectively flipping the spin around the boundary of the superconducting island, as seen in the Hamiltonian for the Toric code. So practically speaking, what does this actually look like? So here we see an example of a simple representation of a series of these quantum islands described by the Kitaev theory in terms of a two-dimensional surface in which the orientation of spins are shown according to the either going in or out of the page here. So this is based on a great deal of, or a lot of work by collaboration, which sought to realize 1D Majorana fermions on current state-of-the-art quantum computers. So for the remainder of the talk, we'll be looking at actual values computed on IBM's quantum computer located in Sherbrooke, Quebec, using KISS-KIT in Python. We are able to realize these codes. So this is for a 3x5 system. So these 3x5 corresponds to the m by n lattice. So m is 3 and n is 5, as we described earlier. So we see that for a given 3x5 lattice, we actually have 12 qubits, and they are given in terms of the quantum circuits seen to the right of the screen. So these circuits really just correspond to applying linear matrix operations to some qubit states in terms of some 4x4 matrices. For a given 3x5 system, we compute the plaquettes and the vertices. So the stars correspond to the vertices, and the plaquettes correspond to the topologically ordered operators that we saw corresponding to the electric particles, and the vertices corresponding to the magnetic particles. And here we see a representation of topological entanglement entropy itself, or a state comprised of multiple entangled qubits. And so basically we're looking at certain sub-representations of the surface and the corresponding entangled entropies associated with each of the values at these sites. So S is the entangled entropy that we saw earlier. So we know, so in our toy model, we know sort of according to this 2D surface what we should expect sort of analytically. And we see that when we run the simulation, or actually collapse the values on a real quantum computer, we are able to actually restore the theoretical value of S within a certain level of uncertainty. So we have only one significant digit, so that allows us a little bit of forgiveness. You can see, though, there does appear to be some fairly considerable divergences as the complexity of the system sort of increases. So, but at least within the scale of our uncertainty, we are able to fairly accurately compute the expectation value in terms of every poly-basis combination. And finally, we can extract the braid statistics. So these braids correspond to entangled electric and magnetic states sort of operated on by these logical gates. We see that with very good accuracy on a simple toric system. So again, this is on a simple 2x3 system, or sorry, a 3x5 system. We're able to quite accurately compute the expectation values of our phase angle, which we would hope from the topological invariance of our model. And so we see that even on contemporary low bit or low qubit scale quantum computer with superconducting modes, we're able to very accurately compute statistics involving abelian anyon braid states given by 1D Majorana zero modes. So this is very promising because it means that the topological approach will be sufficient on various architectures, including photonic and silicon-based quantum computing systems, and it also gives quite a lot of positive impetus to the notion of a sort of invariant-based approach to quantum matter, in which, again, as I sort of briefly mentioned at the beginning, the topological computation state literally corresponds to a new quantum material phase, which is a product of the geometric phase or the Berry phase itself. So this is a very exciting field of both as a very exciting field both as an intersection of physics and scientific computing, because it really emphasizes the physical reality of quantum topological matter, and it extends the notion of what we ordinarily think of as quantum material into the space of computing in a way that's very natural to both mean field theory and sort of these more theoretical interests in sort of formalizing the geometry of certain physical interactions in terms of invariant quantities. So overall, it's a field of research which is very promising, although somewhat difficult to realize. And it is my hope that universal quantum computing will be realized topologically for many of the positive reasons that have been outlined in this talk. And with that, I would like to open the floor to any questions if anyone has any.
Yep.
Yeah, thanks for the talk. But yeah, can you say something more about these like an experimental realization or like possible candidates or approaches
So this is
doing these things?
Yeah, yeah. So these are computed on an actual quantum computer. This is a very simple representation, but it is running on the actual hardware in Sherbrooke. So in terms of experimental realization, as I sort of mentioned, the gist of this talk is really about the way that physical systems themselves can be generalized in terms of invariant geometrical properties. So we sort of took a roundabout, or we sort of did a bit of a horseshoe sort of shape talk in a sense. The notion of the Aronoff-Bohm effect as a observable, experimentally viable phenomena plays a pretty significant role in collider physics, but also in like things like gravity detection and all sorts of other interesting sort of things in which or phenomena in which the system in question is sort of confined in some sense. So basically, the idea here is that there's an analogy between sort of confinement in flux tubes and quantum information. So effectively, the braid becomes a sort of entangled entropic quantity in which the phase values associated with the orientation of the spin vectors basically gives you the ability to order and classify the entire computational topology. So it's in terms. So if you're asking about the experimental evidence of Majorana fermions, for example, I don't know that they will ever be like found in a pure state. Like I think they've already been observed in terms of like bulk densities in superconducting modes in condensed matter physics. So it's fairly likely that the Majorana mode itself will never be found to be like fundamental in terms of like some statistical state corresponding to some like pure quantum information state or something like that. But it's, except perhaps in the case of the neutralino, like I mentioned, and then when that's discovered, that will probably be used to fill in a lot of gaps in band theory and forgive the pun and the sort of material physical material theory. I'm sorry, I'm not sure if I answered your question sufficiently.
No, it's fine. Yeah, I was just kind of curious about different setups, but that does make sense.
Yeah, so I mean, so topological quantum computing could be realized on a variety of computational architectures, like in terms of confined, now I'm struggling to name a few of them, but there are like superconducting uh, cavity theories in which like effectively you have photonic or silicon based quantum processors that have these cavities that allow for some of these anionic states. But it is worth noting that even in adiabatic quantum computing, 1D Majorana modes can be observed. It's really just like a hypothetical quantum computer is basically indistinguishable from a pure, like a perfect hypothetical quantum computer is indistinguishable from a pure information process, which is why the notion of quantized gravity as a computable space-time theory, effectively equivalent to quantum computing, is so attractive. But as to anyone specifically building topological quantum computers, I don't really work on experiment exactly. I'm mostly a mathematical physicist. but they're out there, and for sure, as quantum computing approaches a computing megabit computing capacity, the notion of computational matter as a topological quantum phase determined state will become more and more relevant. There is sort of like a way of going back and forth between these descriptions in this sort of way. I personally just like topological quantum computing because of its natural analogy to mean field theory, and of course, as we heard earlier in many of these talks, there's a great deal of fruitful viability in sort of these icing chain descriptions of energy-based systems. So it wouldn't surprise me in the slightest that there were some corresponding like mathematical formalism that perfectly describes a learning system, and also like topological qubit system. As to the overlap between topological quantum computing and AI, I can't speak to much of that, although I do have some colleagues working in sort of quantum machine learning, but none of them are really that interested in topological quantum computing. Are there any other questions?
Yeah, I just wanted to comment. Yeah, I mean, I've always kind
sorry.
of heard that as like this great, it's scalable, right?
Yeah.
Unlike the normal kind of quantum computing, but it's been there was also Michael Friedman and Microsoft Q and
Yeah.
a lot of effort to build these computers, but at least to my knowledge, none of it has gone anywhere, and none of it has really yielded concrete experimental realizations of like the dream. But like there's been progress and there's been interesting theoretical work from it, is my understanding.
Yeah, I mean, I tend to tell people that we're in sort of like the 1940s or 1930s of quantum computing compared to, say, classical computing. Although we're arriving at the present day, I guess we'll get to 1969, 1970 Unix level, maybe in the next like 15 years or something like that. I think there's a certain degree of viability in certain modes that are, or certain approaches that are being taken, and other ways of looking at quantum computing are sort of more theoretically interesting. Although I do not believe that even in a world in which quantum computing becomes relatively cheap, that classical computing will ever fully be completely replaced, at least not in the consumer reality for like the next like 100 years or so. In fact, a lot of my interests involve classical interfaces with quantum computers and the potential value of these large centralized quantum computing hubs that are accessible via some publicly accessible interface or something like that. Something like KissKit really leaves quite a lot to the imagination. It's really only usable for numerical computing at this point, and because the limitations on the number of potential bits or qubits is quite low, you won't be doing anything too exciting anytime soon. But it is worth noting that the quantum Fourier transformation has a lot of practical uses even now. But I suspect that quantum computing will reach the ability to defeat classical cryptography within the next 10 to 15 years, easy, probably in the next 5 to 10.
Yeah, it seems also like finding applications of quantum computing itself is kind of an open problem insofar as you have cryptography, you have simulating quantum systems, but it's kind of like what else?
A side note to that is just to
Yeah,
say there was a paper done by Goldman Sachs and IBM-Q at one point for Monte Carlo simulations for derivative pricing, and that looked kind of promising.
Yeah, I mean, any sort of predictive numerics will benefit massively from quantum computing. I mean, as I mentioned, when I was studying uh, quantum computing about a year ago, I was like the only particle physicist in the entire group. Almost everyone there was an electrical engineer, and a significant number of them were studying AI slash machine learning in the context of quantum computing. I don't, and I myself have even had the opportunity to ask Yoshua Bengio himself about what he considered to be sort of the potential realizable goals in terms of like adapting quantum computing to adapting deep learning to quantum computing, and he didn't really have much to comment. It's sort of out of his wheelhouse, but I think that as the architecture becomes densely scalable enough that we can have, like, I mean, I think by the time we get to the 10,000 qubit phase, up to the first megabit, megaqubit, you're going to see a lot of really crazy stuff start happening. But as I said, the quantum Fourier transformation works right now, and it's by far the most efficient way to do it, and it can be done on Qiskit or Q or any of these systems.
So if I understood it correctly, so like we distinguish these topological phases with like topological invariants, like Chern numbers, right? And then
Exactly.
those, yeah, and those correspond to this the phases of the Ising model and like the order of the Ising model, right?
Right.
Is is there any like in the classical Ising model, there's like this interesting behavior near criticality where you have these like long distance correlations appear, and was like wondering if there is any connection to like the entanglement entropy, and if there is or any or some other phenomenon.
Yeah, so admittedly, I'm not as into condensed matter as perhaps I should be. It's sort of a little further down the chain for me, below sort of particle physics and high energy field theory. But I can definitely conjecture that the entanglement entropy that we're describing in our model is present in any Ising system, but specifically, like, we're considering the way that the the state operators associated with the quantities on, like, that are so I'm sort of reaching now, but so there's this notion of the superconducting island in Kitaev theory, where effectively you can approximate these honeycomb lattices in terms of like some radial vector coming from either the center or the one of the vertices. And it's so when we talk about entanglement entropy, we're really talking about and in the context of topological quantum computing, we're really talking about the way that, say, qubits encode uh, like physical representations of or their actual space time path histories of these whole anti-whole sort of modes, which are describable in terms of like QED. So basically, coherent information across transformation or configuration change in the state or in the system becomes really relative to keeping track of these coherent information modes. So yeah, I mean, entanglement entropy. So if you're using a quantum description of the system in which you know, as you mentioned, Chern number, winding number, and other topological invariant quantities are relevant, then yeah, like the entanglement entropy effectively describes the overall state statistics of the whole system, and calculating it for specific configurations becomes you know, again, this is a toy model, so it's almost trivial how it's being calculated. But you could imagine that in a qubit state in which you were dealing with some complicated information, such as, you know, encoding a film or like, so coming back to the previous question with regards to practical or experimental realizations of quantum computing and potential future applications, I envision something of an eventual quantum internet in which, you know, classical machines are able to access information by basically generating spin statistics from you know, entangled state vector bundles, which would correspond to anything like that we currently use on the classical internet. So if you could imagine, you know, replacing, you know, having a hash function or something that's determined by measuring the entangled entropy value of you know, a given chunk of quantum information or something, or even a coordinate by coordinate observation of the entropy. You could see how something like that would become really relevant. And also, of course, in mean field theory, the free energy can basically be described in terms of the entanglement entropy as well. So it all sort of goes back and forth on itself. But yeah, I mean, it's anything relevant to the Ising model in general is relevant to sort of this approach to quantum computing, and in a sense, the other way around, because as I said, I have very strong inclinations that effectively material reality works as something of a quantum computer. So we should find basically analogs in nature, especially in self-sustaining systems like, you know, we should see like cosmological quantum computers effectively if we view them on the correct scale. Sorry if that's going off on a bit too much of a tangent.
No, that's very interesting. Like I have to think about it more, but this is very curious, and I'm sort of it's interesting how like this, as I understand it, right, the critical point would correspond to this like non-analytic behavior across like topological phases, so like a singularity, right? And it's just like another very interesting connection between appearance of these non-analytic behaviors and these like interesting properties of information transfer.
Yeah, I just grabbed a copy of Huang's Statistical Mechanics to flip through while you were asking me that. So I flipped to a section on correlation and fluctuation dissipation theorem. Yeah, I mean, I think you're on to an interesting observation. As we know, so in I sort of mentioned Goldstone modes sort of earlier in the talk with regards to Landau symmetry breaking, spontaneous symmetry breaking, and it is worth noting that there's a direct analog of the spin waves in ferromagnetic systems or phonons in, say, lattice crystal-based systems, or in superconductors and electroweak theory, the Higgs mode, all basically describable in terms of the same entropic material process involving some virtual Goldstone mode causing spontaneous state collapse. So again, I didn't prepare to consider such a notion, but I think that looking at the critical point would have some well, of course, it's a superconductor, so it definitely does influence the dynamics of the system for sure. I'm also hoping that topological quantum materials can be achieved at subcritical temperatures as well, given that they are such a stable mode of information storage, but they do require, of course, the notion of perfect fluidity. So it remains to be seen whether quantum computing and superconductivity will always be inexorably linked or not. But for the time being, that seems to be the case. Thank you very much.
Thank you.
Are there any other questions? If not, I'm very grateful to be on the bill with so many marvelous and talented speakers, not the least of which Dr. Schwartz and everyone else. It was truly an honor to be able to present some of my research for you today, and hopefully there'll be another opportunity in the future to perhaps cover some of my more relevant research involving dark matter. I'd hope to get into a bit more of a discussion involving spin ice, since that involves monopole modes in spin liquids. And unfortunately I actually thought this talk was going to end up being a little bit short, and it ended up going a little bit long. So it all kind of worked out. But nevertheless, thank you all very much for your attention. It's getting quite late, I think, for many of you. Thank you all very much for staying for my talk.